it is exceedingly common for the AP exam in May to contain one of the 6 FRQs as a differential equation FRQ. And sometimes that will be the analytic approach like we've already covered, and sometimes it will involve the graphical or numerical approaches that we'll cover in the next set of videos. But this example from 2013 is something that we can do right now before we get to the rest of the differential equation notes. So consider the differential equation dy dx equals e to the y times 3x squared minus 6x. Let y equal f of x be the particular solution to the differential equation that passes through the point 1, 0. Notice that the differential equation that is given is separable because we've got a function in terms of y times a function in terms of x. So we can separate the variables. We're not going to jump into separation of variables yet because it doesn't ask us to solve the differential equation in part A. Notice that we're asked to find that particular solution in part B. So don't automatically jump into separation of variables just because you know that you can. Read the directions and do what it asks you to do. If you do work for part B up here in part A, then the College Board isn't going to give you credit for the work. So part A asks you to write an equation for the line tangent to the graph of f. Again, that's the particular solution that passes through 1, 0. At that point, 1, 0. Okay, we know how to write equations of tangent lines. We need 2 things. We need a point and we need a slope. Hey, we've got a point. The point is x, y is 1, 0. We need a slope. Well, the slope, we know how to find the slope because the slope is given to be dy dx. That's what derivatives are. But we're going to evaluate that at the point 1, 0. Right? So don't forget that dy dx is the instantaneous rate of change of y over the instantaneous change in x. This is the slope of the tangent line. That's what dy dx represents graphically. So it's very easy to evaluate that because they give us a formula for that. We raise e to the y, and then we multiply that by 3x squared minus 6x. And since we know that y equals 0 and x equals 1, then we can evaluate this. E to the 0 is 1, and 3 minus 6 is -3, and therefore we get a slope of -3. So our point is 1, 0, and our slope is -3, so we can say the tangent line is equal to the y value plus the slope times x minus the x value. Okay. Yes, you can definitely write this in a simpler way. Maybe we would write it as y equals -3x plus 3. They're both correct, so either or, and that would be the first part of part A. Maybe instead of writing y equals, I'm going to write t of x. Why not? T of x meaning the tangent line function. So t of x, remember that t of x is approximately equal to f of x at x values close to 1, the local linear approximation. So I'll box in both of these. You don't have to do both of them, but either one is good. So in order to approximate f of 1.2, we know that f of 1.2, let's switch colors here. F of 1.2 is approximately equal to t of 1.2. Well, we know how to find t of 1.2. I'm going to use this first version of this. T of 1.2 is going to be 0 minus 3 times 1.2 minus 1, or 0.2. That's just replacing the x with 1.2. And that gives us negative 0.6. In general, it's easier to use this form because our x values are going to be very close to the given x value. So we're going to multiply our slope times the change in x. Okay. So anyway, we can say that f of 1.2 is not exactly equal to negative 0.6, but it is close to. It is approximately equal to negative 0.6. Now, part B is the new stuff that we just covered in the last collection of videos. So we'll go ahead and do the separation of variables technique here. And we're going to multiply both sides by dx. We're going to divide both sides by e to the y. And we're going to get dy divided by e to the y is equal to 3x squared minus 6x times dx. And when we anti-differentiate both sides of this, we're going to find that the left side, how much space do we have over here? Plenty. We're going to find that the left side is going to be, well, we can just jump straight to the answer if we like to, but remember that this e to the y in the denominator is e to the negative y in the numerator. So if you can do this in your head, great. But I'm going to maybe show a few extra steps here. I'll go ahead and anti-differentiate this side. This is just inverse power rule. And then now that we realize this is e raised to a variable, but that variable is negative y, then we can think about some u substitution and realize, wait a second, okay, that means that if u equals negative y, then du equals negative dy, so we will have that chain rule to pull out a negative out front. E to the u will be the same thing as e to the negative y when we anti-differentiate, and we get that. All right, so that is a general solution to the differential equation. We're asked to find y equals something in terms of x, and we also need to find that particular solution. So at some point along the line, we're going to have to solve for c. I'm going to go ahead and do that now. We could do that later. It's really a matter of preference. I'm going to go ahead and do that now. I'm going to let x equal 1 and y equal 0. So we'll have, on the left side, we'll have negative e raised to the negative 0 equals on the right side, we're going to take 1 cubed minus 3 times 1 squared plus c. So this is negative 1 equals 1, well, 1 minus 3 is negative 2 plus c. So when we add 2 to both sides, we get 1. So the particular solution in this current form is negative e to the negative y equals x cubed minus 3x squared plus my c value of 1. Again, we're looking for y equals a function of x, so we need to solve for y, and that will be the last little piece of this. So I'll divide both sides by negative 1 and get e to the y, or e to the negative y is equal to negative x cubed plus 3x squared minus 1. Then we have to undo the exponent by taking the log, right? Log base e, or natural log of both sides. We'll get negative y equals the natural log of negative x cubed plus 3x squared minus 1. That has to be in parentheses. And then we have to get rid of that negative, so y is equal to negative the natural log of negative x cubed plus 3x squared minus 1. And that is the particular solution to the differential equation that passes through the point 1, 0. It's kind of a mess, but it is acceptable. If you want to get fancy, you can start pulling this negative as the coefficient, as this negative 1 as an exponent of the argument, and then you could say it's the natural log of 1 over this cubic. A lot of people like to do that just because they like to show off about their natural log properties, but I would say the more you mess with your answer, the more likely you're going to make a mistake, so I would just leave it like that. And those two parts were the entire original FRQ on this AP exam. Now, another question they could have asked after this is they could ask, well, if we have approximated f of 1 as negative 0.6, we could ask the question, is that approximation too big or too small? And that's what I added here, is determine whether the tangent line approximation from part A is an overestimate or an underestimate. Now, if we were allowed a calculator, then it would be a process of simply evaluating this expression with x equals 1.2. And that would be an easy thing to do with a calculator. But generally speaking, these questions will be non-calculator questions. So if you were forced to do this without a calculator, then we have to come up with some other way of determining whether this is an overestimate or an underestimate. So remember that a tangent line is a local linear approximation of a curve. So let's say this is the point of tangency. The tangent line in this example is too big, right? It's above the curve on the right side of the point of tangency. It's above the curve on the left side of the tangency. This graph is concave down. So that's going to be, a tangent line is going to give you an overestimate for concave down graphs. For concave up graphs, our tangent line is going to be below the curve everywhere away from the point of tangency. So concave up means we're looking at an underestimate. So we have to look at that second derivative. So what we'll do is we'll start with dy dx equals e to the y times 3x squared minus 6x, the given differential equation. And what we're interested in is the second derivative. So we're going to take the second derivative of our solution. So we're going to take the derivative of our differential equation. This is a product of two variable expressions, so we're going to use the product rule. Derivative of the first is e to the y, but don't forget the chain rule. That's going to multiply by dy dx. Remember, what we're doing is we're taking the derivative with respect to x of both sides of this equation. So we take the derivative of e to the y with respect to x, we have to have that chain rule. Okay, so that's u prime times v. V doesn't change. Okay, so that's the u prime v, and then we're going to do plus uv prime. So e to the y times the derivative of 3x squared minus 6x, which is going to be 6x minus 6. All right, that's our second derivative. We could start doing stuff with this, or we could realize that we could factor out some stuff first. So for example, the e to the y is in both terms, so that's going to be left alone. And then, well, this whole thing is another e to the y times 3x squared minus 6x, but we have another 3x squared minus 6x, so I'll write that as 3x squared minus 6x quantity squared. So that's that first term with the e to the y factored out. The second term with the e to the y factored out is just plus 6x minus 6. All right, and that's not the only way we can write this, but I'll just go ahead and leave it like this. The question about this is this second derivative going to be positive or negative in the realm of this point of tangency? Now remember, the point of tangency is the point 1, 0. So the question is, in this area of 1, 0, where x equals 1 and y equals 0, do we get a positive or negative answer? Well, e to the y is always positive, no matter what y is. So we can kind of not worry about that. We know that e to the y is equal to 1 when y equals 0, so we don't really have to worry about this. We're just really looking at 3x squared minus 6x quantity squared. And that's going to be definitely positive because we're squaring it. And then plus 6 minus 6. 6 times 1 is 6, right? So, so we have something positive times 1 plus 0 times 1. So this is a positive value. So y is concave up at the point 1, 0. So the approximation of t of 1.2, which was equal to negative 0.6, is, well, if we're concave up, we're too small. This is less than f of 1.2. So parentheses.